Okay guys, so the next question gonna deal with a charger. You remember the thing that you come up with the phone in the morning and look at the phone and you see, don't got any battery at all, the battery is died, and this is because you didn't plug it right before you went to sleep. So super capacitors, let's write it, super capacitors can actually help to charge your phone in a few seconds. In a few seconds, you're gonna have 100% full charge phone. And in the next question, we're gonna deal with these supercapacitors. And you can think about it, how important this could be in thinking about transportation, electrical transportation, healthy transportation, and not polluted the air. You can have in the city, you can charge them really fast, and they can go around the city, or for phones and other applications. So the capacitor is actually a plate. Here is a plate, and this plate is connected to some battery. This is how we sign a battery. And here we have another metal plate or conductive plate. Okay, so this is the configuration of a capacitor, and they usually distance apart by D. That's how we sign them, and that's it for now. But the first question I want to ask you is, let's call it question 2.1, is let's first of all see that this charger is not dangerous, right? So let's calculate what is the electric field, the radiation, yeah. What is the electric field from one plate of our charger? Okay, so we can say that we have infinite plane which have some charge density sigma. Okay, let's say it's a constant one, sigma 0. So what is the electric field that we have in space? So to solve that, I see that I have infinite plane, which means I can use symmetry, and I'm gonna choose, let's say, some pipe. Oops, let's do this is as my pipe. This is the area that I choose. I'm gonna use Gauss's law, right? And what does Gauss's law say? He said compare the geometry with the total charge that you have inside. So that look inside. So Gauss's law actually said that E inside the area, the closed area, the volume that I have here, the closed area that I choose, equal to all the charge inside my closed area divided by epsilon 0, right? So the shape that I choose is this, and I know that the all electrical charge is actually going in this direction in case of a infinite plane. We talked about that in the previous tutorials, right? So I have here, going about it a little bit faster because you already know it, but what I'm gonna have, I'm gonna see that this is a dot product, right? And this is a vector, and between here you see that this is, let's do dA in another color. This is purple. It's gonna be the shape of this, of the closed area that I choose, and dA on this configuration always gonna give me 90 degrees, which means the cosines gonna die. But here I'm gonna have the dA also pointing with the electric field, also here. So they have cosines 1. So actually I can say that, let's say that this is a distance L. Okay, this is minus L, right, from here to here. So I can say that E in both places, plus and minus L. So I have 2, they are the same, it doesn't matter. Plus and minus L is actually the area of this hat. And this hat is what? It's pi r squared. If I say that this is r, right? And what is the total charge that I have inside this? What is the total charge? It's actually sigma 0 multiplied by this area. This area is also pi r squared, right? So I can get rid of it, and you can see here that you could choose whatever shape that you want you should only have this straight, you know, it's going out like this, that the dA gonna point 90 degrees to the electrical field, and the head could be any shape that you want. You see that it's falling apart. So E in distance L from the plate equal to, divided by that, equal to what? To a constant, which means this doesn't have any meaning. So I can say this is a constant, const. So E is actually equal to sigma over 2 epsilon, and it's right for any electrical, any distance. Why it's happening? Because I said it's an infinite plane, so wherever I go, it doesn't matter to me how far I am from, it's still infinite plane, okay? So we calculate this, and let's go to the next question.